Hello, folks. I'm Shruti Appiah, and today we're going to be talking about risk-adjusted bonding curves. Let me introduce myself a little bit so we can get a conversation going. So I'm Shruti, and I've been trained as a systems design engineer. Currently, I work as a research scientist with block science, where I'm designing the crypto economics of SwiftChain, as well as I led the research on this work on risk-adjusted bonding curves with the Interchain Foundation. Alongside that, I am also designing Marlo, which is a language for building financial instruments. It's Haskell-based. I'm working with Professor Emeritus Simon Thompson on this one. It's very exciting. And previously, I've also worked with Dabra Labs, who famously built CryptoKitties, but my help with them was around crypto economics of the Flow blockchain that just came out. And before that, I have worked with Consensus, where I led the token engineering research for a year. And then I was also on their primary investment team, where I deployed quite a bit of capital into foundational Ethereum startups. And before that, I also led and initialized the decentralized identity strategy at Okta. And so I've been in the space since 2016. Initially started off with building multi-agent simulations and published a paper on that in 2017 of March. And following that, the work has been all around token engineering design, as well as using simulations and multi-agent models in order to validate if the token engineering economies we build are actually sustainable, resilient, as well as robust. Okay, so with that, let's talk about how we applied these kinds of principles to risk-adjusted bonding curves, right? So let's go through a little bit of a background on bonding curves. So we've typically heard of bonding curves. These are basically relationships that would determine the relationship between the price of a particular token as well as its supply, right? And the most common type of bonding curve is a static bonding curve, where it means if you want to bond into the bonding curve, that means you buy into the bonding curve. It's basically a mechanism to distribute tokens. It has been used several times around, and tokens in this bonding curve are either issued or they are burned through buy and sell actions. So in this risk-adjusted bonding curve, we have deployed a version of bonding curves as well. However, the problem with static bonding curves is that they have a few shortcomings, mainly that once you fix a priori assumptions in the initial part of the system, then you will not be able to change any of that during its execution. So even during the execution of the bonding curve, if you learn anything new about your system that you didn't know about previously, then that cannot be changed, and that can often lead to unintended consequences. And so this is what happens with static bonding curves, right? So let's explore that a little bit further. So if you have fixed a priori assumptions at the initialization of the bonding curve, this means that during the execution of the bonding curve, if you have certain parameters, particularly parameters around risk or parameters around things that will change during the execution, then you won't be able to incorporate those parameters into how the bonding curve works, right? So as a result of that, the risk will accumulate non-linearly, and tokens will eventually get misallocated, and as a result, investors will get a poor return on their investment most of the time. And so during closeout, either investors will get a poor ROI, or occasionally the systemic collapse will, even that kind of a thing might happen. That's relatively rare, but typically the scenario is that investors will get poor ROI. So how we fix this is that is with a risk-adjusted bonding curve, where we tied the success of a bonding curve depends on the execution of the bond, right? And the way we did this is by continuously estimating the bond's likelihood of success, or by continuously estimating the risk that is existing within the bonding curve, and then we dynamically adjust the bonding curve while responding to external as well as internal inputs. And by doing so, we're able to make this bonding curve risk-adjusted, so it's adaptive to external signals such as risk, as well as internal signals such as private beliefs of agents. So as a result of that, what we're able to do here is we're able to match investor returns on investment more closely to what they actually believe so. And we are able to eliminate this whole model of fixed a priori assumptions, because you don't need to make assumptions on parameters such as risk anymore. We're able to change that during the execution of the bonding curve. let's go through an overview of some concepts, right? So the first one that we frequently apply here is we liken economic systems to complex systems because there are quite a few properties of economic systems that mirror the complex systems concepts quite well. The first one is that economic systems are nonlinear. They are not in equilibrium at all because agents have private beliefs, and that leads to certain kinds of changes within the overall system at the system level. They are chaotic, meaning that they're very sensitive to initial conditions. So if you fixed an a priori initial condition about some sort of a parameter, that kind of a thing will have a huge effect as it accumulates over time. So that kind of nonlinear behavior, you see it being called as a butterfly effect. That's what is commonly referred to. So, but basically, at the basis of it, it's a foundational chaotic system, right? And within economic systems, interconnections matter as well. So, and typically in engineering, you learn to take a larger system, you learn to break it down, and then analyze the individual systems without really thinking about the overall system or about other systems and how they interact with each other. However, in this particular economic system, interconnections matter really a lot, and how the agents interact with each other matters quite a lot to how the system functions overall on the top level. And they're also self-organized, meaning that you'll often see things such as the Pareto principle, the 80-20, applied very frequently. You'll see a lot of phenomena occurring that follow that kind of a principle. And they're also in non-equilibrium, like I mentioned before, because of the internal signals, such as that kind of a flux that occurs with agent beliefs. All of the reasoning that happens within the system is through induction. And as a result of that induction, you'll see at the system level, there is a non-equilibrium state, almost always. So another concept that we applied is estimation theory, right? We consider economic games as estimators. This is also a paper that I borrowed from, is written by Michael Zargham. And the way we see the system is basically as the system for the bonding curve is an estimator, right? And we estimate system level properties such as risk by taking into account and collecting information about what actions the agents are taking. So if the actions the agent takes are such that they estimate the risk to be very low, and if they are very positive about the project, we take all of that information, put it into an estimator, and get a system level estimate of some action or of some parameter that exists only at the agent level. So what we do is we're with this estimation theory, we're able to convert agents' internal mental models of certain parameters or of the system into public level, system level information. Another theory that we also borrow from is configuration spaces. This is something that you'll see frequently in robotics, where you have a general state space. This is the space of all the potential configurations that the robot can take, but with constraints. So if we impose any kinds of constraints that have to do with things like the overall laws of the system, the conservation laws of the system, then we're able to constrain that general state space to a much smaller configuration space, thereby making the problem much more manageable. And if we have our solution space much smaller, then it's easier to search there, right? Because it's smaller and there's less computation to do. All right, so with all of these concepts, let's see how we designed our system of risk-adjusted bonding curves. So the first thing we do in any kinds of system design work is we identify the state variables. So we need to characterize the system, right? How are we able to characterize the system? It is through state variables. So we describe the system, the current state of the system, through many aspects of the system that underlie it. So things such as reserve, supply, things that you would see typically in a bonding curve, as well as alpha, which is our risk parameter, and kappa, which is curvature of the bonding curve, as well as the agent-related states. So each agent is modeled with their own individual private beliefs of alpha, of kappa, as well as the risk of the that they think of the system to be. So that's the state variables, and that characterizes the system overall. And then we also need to characterize the agent private beliefs. And so this essentially has to do around building a model around how an agent formulates their private belief of a particular parameter. So whenever you want to make a decision about something, it comes from your private belief, but that belief, that information, also comes from something prior to it, which might have informed it, right? So we formulate that private belief based on either several statistics that the agent obtains in order to make their decisions on actions that they would take, either to place a bond action or a buy action on the bonding curve, or to make an attestation about the risk adjusted with the risk associated with the bonding curve. And then we also model the actions. So the actions within this system are particularly things such as bond and burn, which is usually present in the bonding curve, as well as attest positively for risk or attest negatively against the risk, as well as policies. So policies determine essentially what actions the agents will take depending upon their private beliefs. So this one will map essentially what private beliefs the agents have, which will result in future actions of the agents. So it seems like a rather large problem, right? We're dealing with two different systems here. We're dealing with a bonding curve as well as prediction market, which determines the risk of the particular project or of the system. So in order to make that challenge a little bit simpler, what we did was we constrained everything. We constrained not only the action spaces, but also the state spaces. The way we constrain the action space is that all agents are able to take. So in an unconstrained action space, there exists all actions, right? But we have several kinds of agents within the system. So they will only, and some kinds of agents will only be able to take certain kinds of actions. So we jotted down the permissible actions of these agents, and we were able to thus constrain the action space into a much smaller one. Similarly, we also constrained the general state space. That one was really large. So we applied a conservation function, which is essentially like laws of motion of the system. An apple will not fall upwards if detached from a tree. So similarly to that, there are certain relationships in the system that need to be maintained for it to make any analytical, mechanical sense at the very foundational level. And that's the conservation function that we have here. This one is the conservation function on the bonding curve. And by applying that, we were able to constrain that general state space into a much smaller configuration space, right? Thus making the challenge a far more manageable. All right, so after we did all of that, then we went on to modeling. This was a lot of analytical work, but we also wanted to model it in order to verify certain properties as well as validate certain properties of the system. So what we did was we first modeled, we built a system model of the risk-adjusted bonding curve as a state machine here. So the first one is that we have several different phases here. So you can see all of these different bubbles represent the different phases. The primary phases that we'll be talking about here are the initialization phase, the execution phase, as well as the settlement phase. The execution phase is the longest phase in this one, and you can see that between each of these phases, there are state transitions as well, and these state transitions are only achieved if certain conditions are met that will allow the agents or the system to move between these different states. And we also categorized all of our agents and their roles depending upon what kind of actions they're able to perform. Like earlier, we were talking about the permissible actions, which allowed us to constrain that action space, right? So we constrained that, and the way we were able to do it is by categorizing the different types of agents that exist within the system, right? So based on that, we were able to, develop this type of a taxonomy of different types of agents. All right, now let's examine what kind of mechanisms exist within the system, right? The first one is that of bonding curve. So a bonding curve is this, what we're using here is a static bonding curve in combination with a prediction market. And this prediction market is what helps us estimate the risk associated with the project. And when we're able to combine those things, we're able to obtain a risk-adjusted bonding curve. And that kind of a system will allow us to estimate risk on an ongoing basis during the project's execution and update it based on investor actions or based on agents' actions. So by doing so, we're able to make that bonding curve adaptable, and we're able to make it adapt to essentially what the agents are telling it to do. Right. So we have two actions within the bonding curve here, the general bond to mint as well as burn to withdraw actions. Every agent is able to do this. And we have the prediction market here as well, where agents are able to attest positively. That means they attest saying that the project will not fail. So they're attesting, for risk. And attest negatively, where they're saying basically that they believe that the project might likely fail. So this is a prediction market that which collects information about whether the agents believe the project will be successful or not. And as you can see here, these two actions, the attest positively and negative, these are bond-only actions, so they're only additive. So if an agent wanted to change their position on whether they believe that the project will succeed or fail, they can only add on to the other side. They can't retrieve from the side that they just previously did. So yeah, and that's our prediction market as well as bonding curve. And these are working in combination, right? So this is a hybrid system. It's a hybrid system because both this bonding curve as well as the prediction market are working in conjunction with each other. They have certain properties that interact with each other, and we can see these interaction effects in this explored further. So like what we saw earlier, we were talking about conservation functions, right? And these conservation functions are essentially these relationships that will be maintained throughout the execution of the system, regardless of how the parameters within it move. And the reason why that is because that's the underlying mechanical operation of the system. So it's like essentially a law of motion for an economic system. And those things are maintained here. So we have two invariants here. So the first invariant is invariant V, and this is conserved within the bond and burn system. And then we have invariant I, which is conserved in the attestation mechanism. But between these, invariant I will change when any bond or burn action is taken, and invariant V will change when an attest positive or negative action is taken. So these are only local invariants, as you can see. They are only conserved within their respective mechanisms. So as you can see here, within the prediction market, we have I being conserved, and whenever anyone places an attestation action on risk, then I gets conserved. However, that will change invariant V because it's not conserved under invariant V is not conserved under the attestation mechanism. And similarly, in the bonding curve mechanism, V gets conserved, but that kind of a bond or burn action will induce a change on I. All right, so let's explore a little bit about how we actually adjust for risk, right? Now I think this bit is the novel concept here, as well as a hybrid system and having these two composed systems interact with each other, right? So the way we adjust for risk is by having this mechanism called attestations, right? So attestations essentially allow agents to attest positively, saying that they think that the project will be successful, or they can attest negatively, saying that the project will fail. So what we do is we initially will set alpha, which is the risk parameter, to some amount of value. Here it is initialized to 0.5, which indicates that there's equal likelihood of failure and equal likelihood of success. And then we let the system run, and we let the agents take their actions. So the agent, whenever an agent is test positive, then the alpha will increase. It will go towards 1, where 1 represents that the project will definitely succeed, and all of the agents believe that the project will succeed, and 0 represents that the project will definitely fail. Right, so whenever an agent attests positive, it will go up, and when an agent attests negative, it will go down. And that's how we update alpha. So going more into it, so what happens at the end is that the alpha at settlement, so this is the final phase, right? After the entire project has been executed, at the final time step, we're able to evaluate what that alpha is, and when we find out that alpha, we're able to calculate the agent's payout depending upon what kind of a private alpha they have, as well as how many tokens they have used in terms of attestations. Right, so that way we'll be able to calculate the payout of the agent depending upon whether they tested positively or negatively throughout the execution of the system. So essentially over here, you can think of it as the agents are essentially rewarded for predicting correctly whether the project will fail or succeed. So that's exactly how this game would act as an estimator of alpha. What we did previously was we take in the information about agent actions. So agent actions are their own public information available here. We're not able to have an outlook on their private beliefs because, of course, it is private. But we're able to see what they do, what kind of actions do they place on the system, right? It is a public blockchain. We're able to view that. And so by taking that information, we're able to extract it, put it to an estimator, and allow that estimator to come up with a system-level estimate of the collective aggregate of all of the agent actions. And that way, we're able to estimate this system-level alpha based on the private belief of alpha of all of these multitude of agents. So the agent actions are able to reveal their private belief, and we put that into a system estimator, and then we're able to obtain a system-level estimate of the risk parameter alpha. And so if you want to go more into detail, alpha is updated using a Markov chain update process, which employs essentially a convex combination of the current state alpha as well as the realized alpha upon the agent taking the action, right? And the reason why we use this convex combination is because we want to ensure that there's not a ton of volatility in the system. We want to ensure that whenever an agent places an action, that action, the alpha update that comes out of that action respects the previous alpha, right? It doesn't have to move too wildly from it. So that's the reason why we have this epsilon here, which is the weight on the alpha, and that determines how volatile this particular alpha parameter can be. So if epsilon is really high, then you can expect that the alpha won't move too wildly, and if epsilon is too low, then the alpha is very responsive to agent actions. So you can set your system in any which way that you like. These are the kinds of things that allows a system designer to play around with and essentially change and customize your system according to what's most optimal for you. All right. So based on all of this, we saw a lot of concepts here. We saw a lot of explorations and analytics here. So based on all of this, let's see what our simulation results yielded, right? So for simulation, what we did was we took this analytical model, this mathematical model, and we input it into a CAD/CAD simulation. Now, CAD/CAD is computer-aided design, and it allows us to essentially throw in all kinds of economic models and other models also into state update blocks, and that will allow us to essentially simulate what kind of things will happen as a result of certain in external factors or injections, or how the system will even behave under normal conditions, right? So it's an agent-based simulation tool, so you will be able to see what kind of results come out of your setup as a result of setting it up in a certain way. So let's see what we got as results. Okay, so the first test that we ran was where we analyzed agent payouts in a pure bonding curve as well as a risk-adjusted bonding curve. So we compared against the static bonding curve as well as risk-adjusted bonding curve. So what we saw in the static bonding curve was that agents were typically earning an average payout of close to like 90 tokens, right? You can see here it's like almost everyone's earning about the same, and they're all earning close to like 90 tokens. And remember that in a pure bonding curve or a static bonding curve, the only actions they're able to take are the bond and burn actions, right? And this type of a bonding curve is the one that is more susceptible to systemic collapses or investors not getting a good return on their investment because of fixed a priori assumptions. Now let's see what happens in a risk-adjusted bonding curve. So here you can see that there's a lot more volatility, as in there's a lot more variation within these agent payouts, right? You can see that some of them earn only as much as like 160 tokens, whereas others are earning close to 250 tokens. So the average payout comes out to 200 about, and that's significantly higher than the average payout in the pure bonding curve. And the variation is also a lot more. And the way we can explain this is by saying that the variation is caused due to the ability for the agents to really make more actions that are closer and more accurately reflect what they truly believe the success of the bonding curve to be, right? Whereas here, they weren't able to really do so because there's no way for them to really make any actions based on their estimation of risk, right? Whereas here, in the risk-adjusted bonding curve, you're able to take actions based on risk as well as on your estimate of price. So here is the dynamics are only price, so there's little variability. Whereas here, the dynamics are price as well as risk, and that allows agents to make essentially smarter choices because they're informed with more signals. More information means smarter decisions, and as a result of that, there is more variability. And there's also a higher payout in this case. All right, so we also tested another scenario, right? So we built this project in partnership with our implementation partner, IXO, and with them, they wanted to implement this bonding curve for chimple education. And in that type of a bonding curve, they also wanted to have continuous funding. And by continuous funding, I mean that whenever the reserve goes up, a portion of that reserve gets taken out and gets fed into the project operating funds. And so that way, if Chimple is about to use this.
Hi, so we're almost out of time. Do you want to wrap up on a few last thoughts or answer some questions?
Yeah, sure. I'll wrap up with this slide and then I can answer questions. And we also have secondary markets here so that we disallow burn on the primary market. And you can see here that the scenario where both of them are on are essentially the agents are earning much lesser, but the IXO setup is this one where they have continuous funding on, but burn on primary market is off. And the scenario here with agent payouts is quite good. And so those were our simulation results. If you want to explore further, you can visit our GitHub repo, or you can contact me on Telegram or LinkedIn, or check out my GitHub. And yeah, if you have any questions, feel free to ping me on any of these different channels. I can also look at the questions here and respond to you guys. And with that, thank you all and stay virtual.
So we probably have time for one question.
Okay. So we have 4 questions here. I'll take a read at some of these questions. All right, so I'll take one of these questions because I haven't answered it before. If you want to answers to any of the other questions, there are definitely other talks that I've given on this topic, and you can also contact me afterwards. But there's this one question that I find here quite interesting, which is, what is the criteria for participating in the prediction market? Is it limited by holders of the token represented by the bonding curve, or is it completely public? Is it something that can be parameterized? So the criteria for participating in the prediction market is that the agents hold supply tokens in the bonding curve, right? So an agent should have participated as a prior requirement in the bonding curve in order to be able to participate in the prediction market. And the reason why is because the tokens in the prediction market that you use to make your attestations are supply tokens, which you are able to obtain from the bonding curve. So you see this interesting dynamic here where in order to be able to have any effect on the risk of the project, you need to have some amount of risk in the, you need to have some amount of say or influence on the price first. So that way, you always need to perform a bond action to obtain supply tokens, and then you will be able to get supply tokens in order to make an influence on the risk. So any agent that has had any amount of influence on the risk would have had at least some proportion of that type of an influence on the price market, on the static bonding curve. So you can see how the price is oftentimes more influenced than the risk, because more agents on a whole are participating in the bonding curve than in the prediction market.
All right. This was a really great talk. Thanks so much for your time. We're going to transition to our next session now.
All right. Thanks, folks. Cheers.